Up through Unit 3, we have been practicing finding the derivative as well as using the derivative to find the slope of a line that would be tangent to a curve. Now we will be extending our use and expanding our use of the derivative to describe graphs. So in this first section, we'll talk about how we can use the derivative to describe a graph and where it is increasing and decreasing, as well as what the type of concavity will be. Now, for those of you in physics, these descriptions are slightly different, so we're talking about in calculus. So first of all, by definition, this is our algebraic definition, we're going to let f be defined on an interval and let x sub 1 and x sub 2 denote points in that interval. So I will show you each piece and its corresponding graph. So the function f is said to be increasing on a given interval when f of x sub 1, meaning this y value, is less than f of x sub 2 whenever the point x sub 1 is less than x sub 2. Okay, so what this means in English is that when your x sub 1 point is smaller or lower in value than x sub 2, and the y values are the same in terms of f of x sub 1 is less than f of x sub 2, that means the function is increasing over that interval from this point to this point. Increasing, okay? Then in B, your function is said to be decreasing on the interval if your x sub 1 is less than x sub 2, however, the value for y that corresponds to x sub 1 is greater than the y value that corresponds to x sub 2. So if you take a look here, here's my interval. This is my first x value, this is my second x value, but my y value is greater than the y value here for x sub 2. So therefore, as you plot these points and you graph your function, this function right here is said to be decreasing. In turn, your function is said to be constant over the given interval if your y values are equal to each other over that given interval. Okay, which should make sense here. So we have a theorem, okay, that says let f be a function that is continuous, meaning you have no gaps, no holes, no vertical asymptotes, no jumps on this closed interval from a to b, so a and b are included, and differentiable on that same open interval. Okay, so you can't be differentiable on the endpoints. So what we're saying here is that if f prime of x is greater than 0, meaning you have a positive slope for every value of x in that open interval, then your function is said to be increasing on that closed interval. So again, we're using the slope here. Then they're saying if f prime of x is less than 0, meaning you have a negative slope over that given interval for every value of x, then the function is said to be decreasing on that closed interval. Then the last stipulation would be if f prime of x is equal to 0, meaning your slope is equal to 0, that means you have a horizontal line, okay, going from whatever your x values are in that interval, then the function f is said to be constant over that closed interval. These are really important to remember, and we will show you how to apply them.